Okay, we're gonna continue on with our examples that we had. We had to find the area of the region bounded by those graphs. Let's put those into our calculator and see what we can get here. So I'm going to clear these out. And I'm going to put 2x to the third minus 3x squared minus 5x, and then I'm going to put 5x minus x squared, and I'm going to do a standard zoom so I can see what that looks like. Okay, and this gives us an interesting dilemma, because we're used to, we've had a function on top, but if you notice when we look here, this function at the beginning, the first function, the 2x cubed minus 3x squared minus 5x, is on top, but then it comes up, it comes down, and all of a sudden the other one, the other function, is on top. You can see there's actually two parts here. There's a region here on the left of the y-axis, and then another bigger region on the right of the y-axis. Both are part of it. So there's two ways that we can do that. And first of all, we have to know where they intersect. I'm going to zoom in on this a little bit, so maybe not. Maybe, let's see. Let's just leave it for now. But I need to find those intersection points for sure. So second calc, find the intersection. 5, first curve, second curve. And now get it close to this intersection point over here. Enter. Negative 1.7912. I'm going to write that down. The calculator will disappear. So x equals negative 1.7912. That's the first intersection point. And let's go back to the calculator. We can see our second intersection point. Looks like it's 0. We'll just double check. Second trace, number 1 for value, plug in 0. And sure enough, yep, back and forth between functions. So x equals 0 is our second intersection point, and our third intersection point, second trace, number 5 again, first curve, second curve, and then we got to get close to this intersection point up here. Enter. 2.7912. 2. Sorry about that. 2.7912. Those are intersections. Okay. Now, for the first part, if we can do this with two integrals. There's two ways to do this. One of them is with two integrals. The way we do that is to be the integral from negative 1.7912 to 0. That first region goes from there. And during that region, the cubic is on top. So it'd be 2x cubed minus 3x squared minus 5x minus 5x minus x squared. And then we'd have to have a second integral, which would go from 0 to 2.7912. And then during that time, the 5x minus x squared is on top, and the other one is on the bottom. Don't forget our dx. Okay. Now that's one way of doing it. Probably not the way of choice for me. Because what I would want to do is recognize that I can do the whole thing at once from negative 1.7912 all the way to 2.7912 by simply taking the absolute value of the subtraction. It will make sure that nothing is negative. So if I'm going to do absolute value, it doesn't matter which one goes first. So I'm just going to leave it as it's 2x cubed minus 3x squared minus 5x. That in parentheses, minus, and then 5x minus x squared, and the absolute value to finish that off, dx. And that is the more compact way to do it. Okay? And what you end up with is about 30.166, or they would also accept 30.167 because it would round either way, just as long as you have 3 decimal places. So when you have that region that has the two regions there, and the top changes, then you can do the absolute value to get your answer. Okay? All right. I'm going to do one more example here. One more example, which is find the area bounded by y equals x cubed, y equals negative x squared plus 4, and the x-axis in the first quadrant Alright, so let's look at that. Put it in, we'll put these equations in. Let's clear out what we have. So the first one we have is y equals x to the third. And then we have y equals negative x squared plus 4. And it says it's going to be in the first quadrant, so I'm going to go 0 here and 0 for a y min as well. Then I'm going to graph. Okay. You can see that little skinny there. I'm going to make that a little bit bigger. I'm going to change my window. X max doesn't have to be anything but maybe 3. Let's make it 3. And y max we'll make it 5 because it's awfully small there the way it is. Let's see. Okay, here we go. Alright, so the region we're looking at is this little, looks like the fin of a shark there. Let's draw that region out, find the intersection points. So I'm going to draw that out. It looks like this. Okay, I knew my calculator would disappear. That's okay. It's like this, and then it comes like, that keeps going like that, and then it comes down like this. That shark. We need to find this intersection point. This obviously starts at 0. This one, let's go back. That one is at 2. We can see it there at 2. So if we can just double check, second trace number 1 at 2. Well, that's the first function, and then the second function, sure enough, it's 0. That's the function. That's this function coming down, that x squared coming down. So we have an intersection point. We need to find this is at 2, and now we need to find that intersection point. So we do second trace number 5. First curve, second curve, and there's only one intersection point, but we'll get close to it anyway, just to say we're close to it. Okay. And then hit enter. 1.3145. 1.31.5. So this is x equals 1.3145. Now we have to figure out which function is on top. We know this is x cubed, y equals x cubed, and this is y equals negative x squared plus 4. Wait, either one of them is on top. Either one of them is on top. So what we actually have to do is recognize that we need to split this into this part is only dealing with x cubed, and this part, the second part, is only dealing with the x squared. So in this case we have to split this into 2. So our first function would go from 0 to that 1.3145, and it would be x cubed dx, and then we would add the integral from 1.3145 to 2 of negative x squared plus 4 dx. And we do that, you can put that in your calculator to get the answer, but that's how we would do it. Good.